In this picture, you can find the picture of a vernier caliper. Now we have studied that a vernier caliper is an instrument that can correctly measure lengths up to 2 decimal places of a centimeter or 1 decimal place of a millimeter. Or in other words, the least count of a vernier caliper is equal to 0.01 centimeter, that is 2 decimal places of a centimeter, or this is equal to 0.1 millimeter, that is 1 decimal place of a millimeter. Now let us say we have to measure an item that has a length which is lesser than 0.1 millimeter. What can be lesser than 0.1 millimeter? Let us consider a very thin wire. Now the diameter of a wire can be less than 0.1 millimeter. So in this case, using the vernier caliper will not give us an accurate result. For such measurements, we use a screw gauge. A screw gauge is an instrument like the one you can see in the picture. Now with the help of a screw gauge, we can measure items so thin which cannot be measured using a vernier caliper. So now let us look at the basic construction of a screw gauge. So this is the basic construction of a screw gauge. The different parts of the screw gauge have been labeled out, as you can see. Now at one end of the screw gauge, marked by A, we have the fixed end, also known as the stud. Now this fixed end is marked by A. The other end is B, which is the movable end. Now as you can see, the movable end contains a screw. This screw goes inside a hollow cylinder. Now this screw moves as we move the ratchet, that is the other end of the screw gauge. Now if you notice closely, you will find that there are two graduations on the screw gauge. One of the graduations is present on the sleeve of the screw gauge. If you look closely, you will find that the sleeve is housed inside the hollow cylinder, and the sleeve contains the main scale. If you notice closely, you will find that each small gradation on the main scale corresponds to 1 millimeter. So this is the main scale which is horizontally marked on the sleeve. There is another scale which is marked on the hollow cylinder, also known as the thimble. Now on the thimble, if you look, you will find that there is a circular scale. This circular scale together with the main scale aids us in reading the particular length which we want to measure, which is very minute in most of the times. Now if you notice closely, the entire U frame is supported around the nut marked as N. So as I told you before, that the screw as well as the sleeve is housed within the thimble. Now once we rotate the thimble with the help of the ratchet, we will find that the screw moves in the forward direction. When we rotate the ratchet in the clockwise direction, the screw will be moving out. Now why the screw moves out? In order to understand that, we need to understand the basic working of a screw. So in this picture, you will find a normal screw. If you look closely, you will find that there are certain threads on the body of the screw. These threads ensure that when a screw is turned in the clockwise direction, it enters a particular socket which we want it to enter. If you look closely, you will see that the distance in between consecutive threads is constant, and this is true for any screw. So when a screw rotates, it rotates along the threads, and in each rotation it moves in by one distance in between the threads. Now if you take a close look at the animation, you will find that a screwdriver is being rotated clockwise and the other end of the screwdriver is on the head of a screw. Now once the screwdriver is being rotated in the clockwise direction, you will find that the screw is moving straight into the socket, which is into the door. So we find that when a screw is rotated in the clockwise direction, it moves along its threads and overall it moves parallel to its axis in the linear direction. Now an important term related to a screw. Earlier I told you that a screw has threads along it, along which it moves when rotated in the clockwise direction. Now in between each thread, the distance was constant. So this distance is known as the pitch of the screw. The same is true in case of a micrometer screw gauge. In case of a screw gauge, the pitch is the distance in between each thread of the screw. So this screw, as I earlier told you, is from the end B. It also contains a definite pitch. So how do we define pitch in case of a screw gauge? The pitch of a screw or a screw gauge is the distance moved by the screw along its axis in one complete rotation of its head. So if I consider a screw from the top, that is the top view, and let's say I'm rotating it in the clockwise direction. So one complete rotation in the clockwise direction will ensure that the screw moves in the linear direction. The distance by which the screw moves in the linear direction in one complete rotation is known as the pitch of the screw. Now we consider a standard screw gauge that is commonly used. In this case, the screw has 100 divisions on its head, or in other words, this screw contains 100 divisions. This means that one complete rotation or a rotation of 100 divisions implies that the pointed end of the screw moves by a distance of 1 millimeters. So we are considering a screw gauge where there are 100 divisions on the thimble, that is 100 divisions on the circular scale. So when we are rotating the scale, that is when we are rotating the ratchet and the circular scale rotates along with it, this screw will move in the forward direction by a certain distance. One complete rotation, that is a rotation of all the 100 divisions, ensures that the screw moves forward by 1 millimeters. So we can say that the pitch of the screw is 1 millimeters because that is the distance by which it moves forward in one complete rotation. So now we have the distance being moved by the screw on rotation of 100 divisions of the circular scale, that is 100 divisions on the thimble, and we saw in this case it is equal to 1 millimeter. So what do you think will be the distance moved by the screw in the forward direction if instead of 100 divisions I rotate it by 1 division? By simple unitary method, I will be able to calculate that this will be nothing but 1 upon 100. So 1 upon 100 will be the distance moved by the screw in one division. So 1 upon 100 millimeters is equal to 0.01 millimeters, and this is what we get by simple unitary method. 0.01 millimeters is also equal to 0.001 centimeters. So what can we conclude from this? We can conclude that the least distance that can be measured by the movement of the screw is 0.001 centimeters or 0.01 millimeters, and this is the least count of the screw gauge. As you can see, it can measure accurately up to 3 places of a centimeter, that is 3 decimal places of a centimeter, and 2 decimal places of a millimeter, which is much more accurate than a Vernier caliper. So the least count of a screw is defined as the distance moved by the screw in rotating it by one circular division. So the least count is the distance moved by it in rotating it by one particular division. In the case of the screw gauge that we have considered, the least count is equal to 0.01 millimeters. So we write the distance moved by the screw on rotation of one division as 1 upon 100 millimeters, which is nothing but the least count of the screw gauge. Now as you can see, I had told you earlier that 1 millimeter is the pitch of the screw and 100 divisions is the number of divisions on the circular scale. So we can say that least count is nothing but pitch divided by the total number of divisions on the circular scale. In this case, pitch is 1 millimeter and the total number of divisions on the circular scale is 100. So now let us take a look at a simulation by which we will measure the diameter of a thin wire. So over here, we are going to calculate the diameter of a thin wire. Now we have considered a screw gauge that is slightly different from the one we were talking about. The one we were talking about had 100 divisions on the circular scale and it had a pitch of 1 millimeter, which meant that on rotation of 100 divisions, it moved forward by 1 millimeter. In this case, we have considered a screw gauge that has 50 divisions on the circular scale. And it has been given to us, as you can see here, that 2 rounds, that after rotating it twice, it covers 100 divisions, which is equal to 1 millimeter. So in this case, 1 round implies half a millimeter. So half a millimeter is the pitch of this screw gauge. However, the least count remains the same because least count is nothing but the pitch divided by total number of divisions on the circular scale. So that is equal to half divided by 50, which is nothing but 1 by 100. So the least count of this screw gauge is also 0.01 millimeters. So keeping the wire at the fixed end or the stud, I will now move the movable end or the screw. So notice what happens when I am moving the movable end. I move the movable end till that point such that the object becomes fixed in between end B, that is the screw, and the stud. Now once the object is tightly held in between these 2 points, I will take a look at the main scale as well as the circular scale. So let me first calculate the circular scale reading. If you look closely, on moving it in the clockwise direction, that is the screw gauge, I have reached the 16th mark on the circular scale. This is the 10th mark, as you can see, and this is the 15th mark. So the additional mark that has been reached by the circular scale, the one that corresponds with the horizontal line on the sleeve, that is the main scale, gives us the mark which we have to consider. So in this case, it is the 16th mark. So how can we find out the circular scale reading from this? The circular scale reading can be easily found out by multiplying least count with the circular scale division or the circular scale mark which we had reached after rotating the screw in the clockwise direction. So we found that it was the 16th division and we know the least count is 0.01 millimeters. So 0.01 into 16 gives us 0.16 millimeters. So 0.16 millimeters is the circular scale reading. Now the circular scale reading alone is not sufficient to give us the diameter of the wire. We also need to consider the main scale reading. So let us see how that comes into play. Over here, if you notice, I had told you earlier that the main scale is graded in terms of 1 millimeters. Now if you notice closely, on rotating the thimble with the help of the ratchet, we have reached a point somewhere in between 0 and 1 millimeters. So it is not coinciding with the 1 millimeter mark, neither is it coinciding with the 0 millimeter mark. It is lying somewhere in between. So in this case, we take the reading of the main scale to be 0, and we had already found out the circular scale reading corresponding to the 16th division as 0.16 millimeters. So keeping these 2 things in mind, let us see what the reading comes out to be. The total reading, that is the diameter of the wire, will be given by the main scale reading as well as the circular scale reading. So that is nothing but 0, that is the main scale reading because it lies in between 0 and 1, plus the circular scale reading, that is equal to 0.16. So the total reading will be 0.16 millimeters, and this is the diameter of the wire, as I will now again show you in the simulation. So over here, if I consider this particular calculation, I will find that the answer is indeed 0.16 millimeters. And as I showed you, 0.16 millimeters is the diameter of the wire, which we found out by calculation. Now let us get into some technical aspects for the screw gauge. Over here you will find that the horizontal scale, the horizontal marking of the main scale is coinciding with the zero of the circular scale. So in this case, on rotating the screw till its final point, that is when the screw touches the stud, if we find that the zero mark coincides with the baseline of the horizontal of the main scale, then we say that it has no zero error, or in other words, it is free from zero error. But what happens if such is not the case? Now a situation may arise that when the screw is absolutely touched against the stud, the zero of the circular scale does not coincide with the horizontal of the main scale, that is the baseline of the main scale. The zero might lie either towards the bottom or towards the top. So these are two cases separately which we need to consider. In the first case, this is known as a positive zero error, and in the second case, it is known as a negative zero error. So let us see how we can correct a positive zero error as well as a negative zero error. In this, we have considered that the zero is lying below the baseline of the horizontal or the main scale. This indicates positive zero error. Now, consider what happens over here. You are rotating the hatchet and the thimble is rotating along with it. So when the zero is not coinciding with the baseline of the main scale, it means that the object is not as thick as is made out by the circular scale. So it means that we are getting a reading that is more than the actual reading. So we have to subtract this error from the reading given to us. So here we find that the zero mark lies below the line of the main scale. In order to correct the zero error, we first calculate the positive error. Now the positive error will be given by the circular scale reading, that is the circular scale division, multiplied by the least count. Now once we get this, we have to subtract this. We subtract this from the total reading, that is positive error minus the total reading, and this gives us the true diameter. We are subtracting positive error because when we had rotated the screw gauge in the clockwise direction, we found that the reading is more than what we actually wanted. In a similar manner, we can also correct negative zero error. Now negative zero error takes place when the zero mark lies above the baseline of the main scale. So this means that after rotating the screw gauge in the clockwise direction, we have obtained a reading that is less than what we had set out for. So in order to correct this error, we need to add the error value to the total reading which we get. So how do we find out the negative error? The negative error is nothing but the circular scale reading that we get multiplied by the least count of the screw gauge. So this gives us the negative error, and if I simply add the negative error to the total reading that I get from the screw gauge, I will get the true diameter that I had originally set out for, free from error.